Hi everybody. The purpose of this video is to help you on questions 7 through 13 of your homework and also the challenge question. In these questions we're asked to write a rational function with the given properties, and we're going to go through two examples here. The first example is a little easier than the second. The second one's sort of like the challenge problem. So in our first example, we're asked to write a rational function that has x-intercepts at -3 and 4, vertical asymptotes at x equal to -4 and x equal to 5, a hole at x equal to 0, and a horizontal asymptote at y equal to 2. So we're going to start with our x-intercepts. Remember that the x-intercepts occur at zeros of the numerator that do not appear as zeros in the denominator. So I'm just going to build a rational function with these properties. It should be equated to 0 in the numerator when x is equal to -3, and I'm going to achieve that by using x plus 3. If I were to plug in -3 for x, -3 plus 3 is equal to 0, and that would equate the numerator to 0. And we also have a x-intercept at +4, so I'm going to achieve that by using x minus 4. That way, if I plugged in 4 for x, 4 minus 4 is equal to 0. The rule for the vertical asymptotes is very similar. It is vertical asymptotes occur at zeros in the denominator that do not appear as zeros in the numerator. So we want a 0 in the denominator when x is equal to -4, and we're going to achieve that by using x plus 4. That way, if I were to replace x with -4, -4 plus 4 is equal to 0. And we also want a vertical asymptote at x equal to 5. And we're going to achieve that by using x minus 5 here. That way, if I replaced x with +5, 5 minus 5 is equal to 0. So far, this thing has two x-intercepts at -3 and +4, and it has two vertical asymptotes at -4 and +5. We also want there to be a hole at 0. A hole is a point of removable discontinuity, and it occurs at values of x that appear as zeros in both the numerator and the denominator. And we can achieve that just by using a regular x. That way, if I replaced x with 0, it would equate the numerator to 0, it would equate the denominator to 0, and that appears both in the numerator and the denominator. Finally, we want there to be a horizontal asymptote at y equal to 2. There's three possibilities for horizontal asymptotes. When the degree of the numerator is less than that of the denominator, there is a horizontal asymptote at y equal to 0. When the degree of the numerator is equal to that of the denominator, there is a horizontal asymptote at the ratio of the coefficients of the highest degree terms. So you could take the leading coefficient of each, the numerator and the denominator, divide them, and that would give you the location of the horizontal asymptote. That's when the degrees are equal. In this case, we want there to be a horizontal asymptote at y equal to 2. So right now, the leading coefficient is 1 and 1, and 1 divided by 1 is certainly not 2, and we want to force it to be 2, so we're just going to change this one to a 2. That way, 2 divided by 1 is equal to 2. You could have also achieved the same thing by putting a 4 up here and a 2 down here, or anything that divides the 2. So we're just going to use 2 and a 1 down in the bottom. And the only other rule for horizontal asymptotes is that if the degree of the numerator is higher than that of the denominator, there is no horizontal asymptote. So just to verify that this is in fact correct, I graphed it in my other program here. I have 2x multiplied by x plus 3, x minus 4. And in the denominator, I have x multiplied by the quantity x plus 4 multiplied by the quantity x minus 5. You can verify there is a 0 at -3 and +4. there is a horizontal asymptote at y equal to 2, and there are two vertical asymptotes located at -4 and +5. The hole at 0 you can't really see in this program, but there is a point of removable discontinuity here at x equal to 0. Alright, let's move on to the next example. In this problem, we're asked to create a function with no x-intercepts, a vertical asymptote at x equal to 2, no holes, horizontal asymptote at y equal to 1. So we're going to just start with our fact that it has no x-intercepts. So there are no zeros that appear in the numerator that do not appear in the denominator. There is a vertical asymptote at x equal to 2. So I'm going to achieve that vertical asymptote by using an x minus 2. And that way, if I plug 2 in for x, 2 minus 2 is 0, and that would equate the denominator to 0. And there are no holes, so there are no zeros that appear in both the numerator and the denominator. And a way that you can force there to be no x-intercepts is by understanding that the x-intercepts are values of x that equate the numerator to 0. And one way that you can achieve this is by just putting a number up there. And that would make sure that there's no x-intercepts because 2 is just not going to equal 0. But right now, the horizontal asymptote would actually be at 0 because the degree of the numerator is less than the degree of the denominator. We need the degree of the numerator and denominator to be equal because there's a horizontal asymptote at y equal to 1. So I need this degree to be equal to this degree. Could I use regular x? Let's see. Well, that would actually have a 0 at 0, even if I put a number in front of it. It doesn't matter. It would still be equated to 0 when I plug in the number 0. So one way that I can force it not to equal 0 is by squaring it and then adding a number. In fact, what that forces it to be is positive. Any number when squared and then added by a positive number is equal to a positive number. But now I have the issue where the denominator no longer has the same degree. So what I'm going to do, so I don't create another vertical asymptote, we only want that one vertical asymptote at 2, I'm going to use another one of these identical terms, or these identical binomials, x minus 2. And what we have here is a situation where there's no holes because there's no 0 that exists in both the numerator and the denominator. There is a vertical asymptote at positive 2, and there's a horizontal asymptote at y equal to 1. Because if I take my leading coefficient here, my 1, and I divide them, I get positive 1. Alright, so that is a rational function that satisfies those properties. Let's look at the graph of it just to verify. X squared plus 1 divided by x minus 2 multiplied by x minus 2. Turn off this previous one. Alright, so x squared plus 1 divided by x minus 2 multiplied by x minus 2. So let's just verify. There is no x-intercept. You could see clearly that this green function never crosses the x-axis. There is definitely a vertical asymptote at x is equal to 2. You can see that it approaches that. And there is a horizontal asymptote at y equal to positive 1. And it doesn't look like there's any holes. So this is a function that satisfies those properties. Alright, thank you for watching. I hope this helps you on your homework a little bit, and feel free to ask me any questions in Google Classroom. We're going to have a video meeting later this afternoon. I hope to see some of you there. Thank you.